Stone Age hunter-gatherers from various regions worldwide commonly used OES beads as decorative items, gifts, and goods for exchange. Research indicates that there are generally two primary pathways of manufacturing these beads. The drilling techniques in OES beads production provide valuable insights into the technological knowledge and adaptive strategies of Stone Age hunter-gatherers, contributing significantly to our broader understanding of human behavior ecology. Relying solely on archaeological records make it nearly impossible to fully reconstruct past human activities. Experimental studies provide crucial supplementary evidence that helps researchers infer ancient human behaviors. The goal of this experiment is to establish a reference collection of modification traces of various drilling techniques, documenting features such as the morphology of the cup parameter, and the position of restriction may help improve the identification and interpretation of the drilling methods of archaeological OES beads assemblage.
We tried a series of drilling techniques that we aim to replicate in our experiments. Number 1, a single direction drilling technique, in which the drillway is made by consistently drilling from one side of the eggshell in a single direction. Number 2, a double direction drilling technique, where drilling starts from both sides of the eggshell. Number 3, the hand drilling technique. For the hand drilling technique, we applied the incomplete form of drilling, sometimes referred to as twisted drilling, and the complete form, or the multi-rotary drilling. The incomplete form of drilling represents a limited rotational motion, while the complete form of drilling uses full circular rotations. In experiment, we use slender jade owls, which are easy to rotate a full circle, and short lithic points made of chert and obsidian, which can only conduct approximately half a rotation each time. Number 4, a hafted drilling technique. This is a method where the drill bit is hafted to a bow drill, trying to simulate more complex tool use in the past.
Various tools can be employed to perforate ostrich eggshell beads. Research by Sherwood and Forsman suggests that lithic tools may have been the most effective option for drilling ostrich eggshell beads when metal tools were unavailable. Lithic tools outperform other materials including wood, bone, enamel, and quill in terms of durability and efficiency. Thus, we chose lithic points and jade owls in our experiment.
To accomplish this experiment, we needed some ostrich eggshell fragments, several obsidian chert points, 2 jade owls, and a bow drill. Dr. Fromm helped us purchase them online. We drilled 8 test pieces before starting the real experiment to practice some drilling techniques. Thus, we have a relatively high success rate during the real experiment with only 1 broken piece.
During the experiment, we recorded the time for each specimen, and we ended up drilling through 12 pieces successfully. These pieces include 3 hand drill specimens done by chert points in complete rotation of drilling, 3 hand drilled specimens done by obsidian points in complete rotation of drilling, 3 hand drilled specimens done by jade owls, complete rotation of drilling, 3 hafted jade owls, bow drilled specimen, complete rotation of drilling.
We carefully collected and documented not only the specimens, but also the tools used for each specimen, including the broken tips of the jade owls to help future use-wear analysis of the drill tips. After drilling, we used the Keynes microscope to document all the specimens. The Keynes microscope system is equipped with built-in focus stacking capabilities and integrated photogrammetry. It allows not only the capture of high-resolution composite images, but also the generation of accurate 3D models for detailed morphological studies. Focus stacking is a photographic technique that combines multiple images of the same object, each taken at a different focal depth, to produce a single image with sharp focus across the entire field. This method can overcome the depth of field limitations of traditional single capture photography, where only a single focal plane is sharp and other areas appear blurred. By using the Keynes microscope, we can see the scratches inside the drillway and the marks left on both sides of the eggshell surfaces by the tools. However, because the 3D modeling capability of the Keynes microscope relies on photogrammetry, any area not visible or not clearly visible in the captured images will not result in high-quality 3D reconstructions. Consequently, for some specimens, we are unable to generate complete 3D models of the drilled pathways, particularly for specimens drilled from both sides.
So we applied micro-CT scanning to our specimens. Dr. Brendan Mercado and Jake Christensen helped us accomplish the micro-CT scanning process. And here is what we get.
To study the morphology of the drillway, we measured the diameter of the cut perimeter and the position of the restriction. We calculated the ratio of the position of restriction to the cut perimeter of each drilled way. A higher ratio suggests that the perforation is closer to a cylindrical form, while a lower ratio indicates a more conical shape. We also visually classify the shape of the position of restriction into irregular, intermediate, and regular by looking at both the specimen and the images taken by the Keyence microscope. We measured the thickness of each specimen and would like to see if there is any correlation between drilling time and the eggshell's thickness. The results show that when drilling starts from one side, regardless of whether it begins from the outer surface or the inner surface, the ratio of the position of restriction to the cut perimeter exhibits consistency. Comparing drilling techniques and materials, hafted drilling produced the highest ratios, followed sequentially by hand drilling with jade, obsidian, and finally chert, which yielded the lowest ratios.
The micro-CT scan reveals that the drillways of the specimens that were drilled from both sides of the eggshell produced discontinuous cups or two misaligned segments of the drillway. This is different from the specimens drilled from a single side, which display a continuous drillway.
The results also demonstrate distinctions in the shape of the position of restriction, corresponding to different drilling tools and techniques, based on the classification of Keyence microscope images. We found that the perforation hand-drilled with chert points and incomplete rotation exhibit irregular shape. Those hand-drilled with obsidian points and incomplete rotation showed intermediate regularity. And jade owls produced the most consistently regular shape regardless of hand drill or hafted drilling by a bow drill as a result of complete rotation of drilling. No clear relationship can be established between thickness and time. This could be due to our small sample size. Besides, different drilling techniques and tools also impacted the efficiency of drilling. For example, hafted bow drilling is generally faster than hand drilling. However, it often creates breakages and debris around the cup parameter. These are the result of our preliminary study. For future research, we hope to make more specimens to increase our sample size, so we can run a prediction model of the drillway morphology of OES beads and apply it to archaeological assemblages. Follow us for further results of our experimental archaeology project related to the drilling techniques of OES beads. See you next episode!